The greatest mind of the ancient world died in a pool of his own blood, killed by a Roman soldier who didn't know and didn't care that he'd just murdered the man who could have changed the course of history. Archimedes spent his final moments not begging for his life, but scribbling geometric diagrams in the sand, so absorbed in mathematics that he barely noticed the sword coming down. This wasn't tragedy, this was inevitability, because Archimedes lived on a different plane of existence than everyone around him, seeing patterns in the universe that wouldn't be understood again for nearly 2,000 years. We're going to trace his life from beginning to end, from the streets of Syracuse, where he was born, to the moment that sword fell. You'll see how one man's obsession with circles and levers built war machines that held off the greatest army on earth, how his discoveries in a bathtub created principles that still govern every ship that floats, how his calculations came within a hair's breadth of inventing calculus 18 centuries before Newton, and how the same brilliance that made him immortal also made him vulnerable in ways he never understood. Syracuse in 287 BC was not Athens. It wasn't the philosophical centre of the Greek world, wasn't producing the sculptors and playwrights that everyone talked about. What it had was money, serious money. The city sat on the eastern coast of Sicily, controlling trade routes between Greece and Carthage, between the old powers and the new. Ships crowded the harbour. Merchants shouted in half a dozen languages. The smell of fish and salt water mixed with the scent of spices from Africa. Into this commercial powerhouse, Archimedes was born. His father, Phidias, was an astronomer, not a profession that typically generated wealth, but in Syracuse it meant something different. The rulers needed accurate calendars for festivals, needed to predict eclipses to maintain their authority, needed someone who could navigate by the stars. Phidias had a position at court, which meant the family lived comfortably, if not lavishly. We know almost nothing about Archimedes' mother. Ancient sources don't mention her name, her family, or anything else. She's simply absent from the historical record, erased by the casual sexism of classical biography. What we do know is that young Archimedes grew up in a household where studying the sky was normal work, where numbers weren't mysterious but tools, where questioning how things worked was encouraged rather than punished. The boy showed promise early. Too early, probably. There's a particular kind of child who asks why compulsively, who can't accept because that's how it is as an answer, who needs to understand the mechanism behind everything. Archimedes was that child amplified to an almost pathological degree. He didn't just want to know how the lever worked. He wanted to derive the mathematical principles governing all levers everywhere. He wasn't satisfied with knowing that boats float. He needed to understand exactly what determined whether something would sink or swim. His father recognized something unusual was happening. Phidias taught his son everything he knew about astronomy and mathematics, then admitted he'd reached his limit. The boy needed more. At some point in his teenage years, probably around 15 or 16, arrangements were made. Archimedes would travel to Alexandria. Alexandria. The name alone meant everything to an ambitious young scholar in the Greek world. The Library of Alexandria held more scrolls than any other collection on Earth. The museum, despite its name, wasn't a building full of artifacts, but a research institution where the brightest minds gathered to study, argue, and push the boundaries of knowledge. Euclid had taught there decades earlier, and his geometry textbook was still the standard. The city attracted mathematicians, astronomers, physicians, and engineers from across the Mediterranean. The journey from Syracuse to Alexandria meant weeks at sea. Archimedes would have sailed south along the coast of Sicily, then east to the African shore, watching the water and probably already thinking about displacement, about why the ship sat at a certain depth in the water, about the relationship between the weight of the vessel and the weight of the water it pushed aside. He didn't know yet that this idle curiosity would later become one of his most famous discoveries. Alexandria must have been overwhelming. Syracuse was prosperous, But Alexandria was cosmopolitan in a way no other city could match. The population approached 500,000. The Pharos lighthouse, one of the 7 wonders of the ancient world, guided ships into the harbour. The royal quarter held palaces and gardens, and everywhere, always, there were scholars arguing about mathematics, about astronomy, about the nature of reality itself. Archimedes threw himself into this world with the intensity that would characterize his entire life. He studied under the successors of Euclid, mathematicians who were extending and refining the master's work. He learned the latest developments in geometry, the field that would become his primary obsession. He met other young scholars who would become lifelong friends and correspondents. 2 names matter here: Conon of Samos and Eratosthenes of Cyrene. Conon was the older mathematician who became Archimedes' closest friend. They would exchange letters for years, discussing problems, proposing solutions, challenging each other's work. When Conon died, Archimedes was genuinely devastated. One of the few times we see clear emotion in the historical record. Eratosthenes was different. Brilliant, certainly. He would later calculate the circumference of the Earth with shocking accuracy, using nothing but shadows and geometry. But there was always a competitive edge between him and Archimedes, a sense that they were both reaching for the same prize and only one could claim it. Archimedes would later send Eratosthenes mathematical problems, some with deliberately false solutions, just to see if his rival would catch the errors. It was the ancient equivalent of academic trolling. The education at Alexandria wasn't just theoretical. The Ptolemaic rulers who controlled Egypt needed practical applications for all this mathematics. They needed better siege engines, more accurate catapults, improved water-lifting devices for irrigation. The museum wasn't an ivory tower. It was a research and development centre for a military power. This is where Archimedes learned to move between pure mathematics and engineering, between abstract proofs and machines that actually worked. He would spend hours deriving geometric theorems, then walk down to the harbour to watch ships being built, studying how the hulls were shaped, how the cargo was distributed, how the whole thing managed to stay afloat despite weighing tons. But something was pulling him back towards Syracuse. His father was aging. The city was entering a dangerous period politically. Rome was rising to the west, Carthage was powerful to the south, and Syracuse sat between them, like a piece of meat between 2 dogs. The rulers would need every advantage they could get, every weapon, every innovation. A mathematician who understood both theory and practice would be valuable. More than that, though, Archimedes seems to have genuinely loved his city. For all of Alexandria's sophistication, for all the intellectual stimulation it offered, Syracuse was home. The harbour where he'd played as a child, the streets he knew by heart, the particular quality of light on the water at sunset. These things mattered to him in ways that pure logic couldn't explain. He returned to Syracuse in his early 20s, probably around 263 BC. The city he came back to was tense. King Hero II had recently consolidated power, but threats surrounded the kingdom. Pirates raided the coast, rival cities plotted, and the shadow of Rome grew longer every year. Archimedes arrived with a reputation. Word had spread from Alexandria about the young mathematician who could solve problems others couldn't even formulate properly. Hiero, who was nobody's fool, recognized value when he saw it. He offered Archimedes a position at court, something between royal mathematician and chief engineer. The salary was generous. The working conditions were ideal. Archimedes could pursue pure research while also applying his knowledge to practical problems when needed. This was the deal that would define Archimedes' life. He would split his time between the abstract and the concrete, between proving theorems that wouldn't be fully appreciated for centuries, and building machines that would save Syracuse from invasion. He was neither fully philosopher nor fully engineer, but something in between that the ancient world didn't quite have a category for. His first major project for Hero demonstrated exactly this dual nature. The king had commissioned an enormous ship, the Syracuse, intended both as a cargo vessel and a demonstration of Syracuse's engineering capabilities. The problem was launching it. The ship was so massive that it wouldn't budge using conventional methods. Workers strained, oxen pulled, nothing moved. Archimedes studied the problem and saw it as pure geometry. He understood that a lever multiplied force, that a small force applied at a great distance from the fulcrum could move a large weight close to the fulcrum. The mathematics was straightforward. The practical application was more complex. He designed a system of compound pulleys and levers that allowed a single man, possibly Archimedes himself, to launch the ship by pulling a rope. The demonstration became legendary. Sources describe Hiero sitting in wonder as this mathematical wizard single-handedly moved a ship that hundreds of men couldn't budge. Archimedes supposedly declared, "Give me a place to stand, and I will move the earth." It's probably apocryphal, too perfect a quote to be real, but it captures something true about his confidence. He understood mechanical advantage at a level that seemed almost supernatural to observers. But even as he was building machines and impressing kings, Archimedes' real passion lay elsewhere. He wanted to understand circles, completely, perfectly, in a way no one ever had before. The problem was that circles were inherently tricky from a mathematical standpoint. They weren't made of straight lines. You couldn't measure their circumference directly. The relationship between the diameter and circumference, what we now call pi, was known to be constant, but its exact value was maddeningly elusive. Previous mathematicians had approximated it. Archimedes wanted precision. He developed a method that was simultaneously brilliant and tedious. He would inscribe a polygon inside a circle and circumscribe another polygon outside it. The circle's circumference had to fall between the perimeters of these two polygons. Then he would double the number of sides on each polygon, getting closer to the true value. Then double them again. He started with hexagons, 6 sides, then 12, then 24. He kept going, calculating the perimeter of each polygon until he reached 96-sided figures. The arithmetic involved was crushing. No calculators, no computers, just a man with a stylus and a wax tablet working through hundreds of calculations, any one of which could contain an error that would invalidate everything that followed. When he finished, Archimedes had proven that pi was greater than 3 and 10^71, but less than 3 and 1/7. In modern decimal notation, that's between 3.1408 and 3.1429. The actual value is 3.1416. He'd nailed it to within a fraction of a percent using nothing but logic and patience. This was the Archimedes who would change mathematics forever, the man who saw problems no one else even recognized, and then solved them with methods that wouldn't be fully understood or improved upon for nearly 2 millennia. But outside his study, the world was moving in dangerous directions. Rome was expanding. The republic that would become an empire was consuming the Mediterranean world piece by piece, and Syracuse, wealthy and strategically positioned, was exactly the kind of prize that attracted Roman attention. The First Punic War had ended in 241 BC, with Rome victorious over Carthage. Syracuse had managed to stay neutral, but neutrality was becoming a luxury the city couldn't afford. The Mediterranean was dividing into spheres of influence. You were either with Rome, or you were eventually against Rome. Hiero understood this. He'd spent decades keeping Syracuse independent through careful diplomacy, knowing when to bend and when to stand firm. He'd allied with Rome when it served Syracuse's interests. He'd maintained trade relationships with Carthage. He'd played the great powers against each other with the skill of a man who knew his city's survival depended on never appearing too threatening to anyone. Archimedes probably paid minimal attention to any of this. Politics was noise. Geometry was truth. While Hiero negotiated treaties and managed alliances, Archimedes was solving problems that would outlast every empire. His work on the sphere and cylinder consumed years. The question seems simple. What's the relationship between a sphere and the cylinder that exactly contains it? You can picture it easily. Take a sphere, put it inside the smallest cylinder that will hold it. The sphere touches the cylinder at its widest point. The height of the cylinder equals the diameter of the sphere. What Archimedes proved was that the volume of the sphere is exactly 2/3 the volume of the cylinder. The surface area of the sphere, including its circular ends, is also 2/3 the total surface area of the cylinder. This 2/3 ratio wasn't obvious. It wasn't something you could see by looking. It required proof, and the proof required methods that Archimedes essentially had to invent. He used what we'd now call integral calculus, though he didn't call it that. He divided the sphere and cylinder into infinitesimally thin slices, compared the areas of corresponding slices, and then added them all up. The technique was so far ahead of its time that it wouldn't be properly formalized until Newton and Leibniz did it 2,000 years later. When Archimedes finally completed the proof, he considered it his greatest achievement. He requested that when he died, a sphere inscribed in a cylinder be carved on his tomb. That's what he wanted to be remembered for. Not the machines, not the military inventions, the geometry, but the machines were about to become very important. In 215 BC, everything changed. Hero died after ruling Syracuse for 54 years. His grandson, Hieronymus, inherited the throne. The kid was 15 years old and convinced of his own brilliance. Hiero had maintained Syracuse's alliance with Rome through patience and pragmatism. Hieronymus decided Syracuse should switch sides. He opened negotiations with Carthage, which was gearing up for the Second Punic War under Hannibal. The logic seemed sound to a teenager. Hannibal was winning battles in Italy. Rome looked vulnerable. Carthage was offering generous terms. Why not back the winner? The decision was catastrophic. Within a year, Hieronymus was assassinated by his own people. Syracuse descended into political chaos, different factions supporting different foreign powers. The city lurched between pro-Roman and pro-Carthaginian governments. The situation was unstable, violent, and exactly the kind of mess that gave Rome an excuse to do what it wanted to do anyway. In 213 BC, the Roman general Marcus Claudius Marcellus arrived with an army and a fleet. The message was clear. Syracuse would submit to Roman authority, or Syracuse would be destroyed. The city prepared for siege. Walls were reinforced, food stockpiled, weapons distributed, and someone, probably a desperate military commander who'd run out of conventional options, approached the 75-year-old mathematician who'd spent his life thinking about circles and asked if he could help defend the city. Archimedes said yes. What followed was one of the strangest episodes in military history. The siege of Syracuse turned into a nightmare for Rome, because a mathematician decided to apply his understanding of mechanical advantage to the problem of killing people. The Romans attacked from land and sea simultaneously. Standard procedure, overwhelming force applied from multiple directions. Marcellus had catapults, siege towers, soldiers trained in every aspect of assault warfare. He expected the walls to fall within days. They didn't fall. Something kept happening that the Romans couldn't explain. Their siege towers would approach the walls. Suddenly, massive stones would rain down from above with devastating accuracy. The towers would collapse. The soldiers would scatter. Catapults firing from the walls hit Roman ships at impossible distances. The projectiles arced through the air with precision that suggested someone understood trajectories better than anyone had a right to. Then there were the cranes. Mechanical arms would extend over the walls, drop grappling hooks onto Roman ships, and lift them partially out of the water. The ships would tilt, men would fall overboard, and then the crane would release them and they'd crash back down, often capsizing. Another device, sources describe it as an iron hand, would grab the prow of a ship, lift it up, and smash it back down. Ships were sunk without the Romans ever seeing who was operating these machines. The Roman soldiers began to panic. Plutarch, writing centuries later, described their fear. Any rope or piece of wood appearing over the wall would cause soldiers to flee, shouting that Archimedes was aiming some engine at them. The siege that should have lasted days dragged on for months. Marcellus, one of Rome's most experienced generals, was being humiliated by an old man with a lever. The frustration in the Roman camp must have been extraordinary. They could see the walls, they could see the city, they just couldn't get inside because mathematics kept killing them. Archimedes hadn't invented war machines from scratch. Catapults existed, cranes existed, grappling hooks existed. What Archimedes brought was understanding. He knew exactly how far a projectile would travel, given a specific angle and force. He knew precisely how much weight a lever could move, based on its length and fulcrum position. He could calculate load distribution, stress points, mechanical advantage. He turned warfare from an art based on experience and intuition into something approaching engineering. The Romans eventually adapted. They stopped trying to assault the walls directly and settled in for a long siege, cutting off supply lines and waiting for starvation to do what their weapons couldn't. Months became years. Syracuse held out, but the city was dying slowly. In 212 BC, after 2 years of siege, Marcellus finally got his opportunity. A Roman spy identified a weak point in the defences. A section of wall was less heavily guarded during a local festival. The Romans attacked at night. The element of surprise worked. They got inside. What followed was the standard procedure for ancient siege warfare. Once walls were breached, soldiers were essentially given permission to loot, kill, and burn. Marcellus had specifically ordered that Archimedes be taken alive. The general understood he was dealing with someone valuable. You don't kill a man who can build machines that sink your ships, but orders get lost in the chaos of sacking a city. A Roman soldier, probably young, definitely following standard protocol, found an old man drawing geometric figures in the sand. Sources disagree on exactly what happened next. Some say Archimedes was so absorbed in his mathematics that he didn't notice the soldier. Some say he asked for a moment to finish his proof. Some say he told the soldier not to disturb his circles. What's certain is that the soldier killed him. Marcellus was reportedly furious when he learned. He'd wanted to parade the great Archimedes through Rome, to show the people that Rome had captured the genius who'd held them off for 2 years. Instead, he had a corpse and a city full of plundered treasures that suddenly seemed less impressive than what had been lost. The irony is brutal. Archimedes survived 2 years of siege warfare, 2 years of being Rome's primary target, only to die because a soldier didn't recognize him and didn't care about geometry. He was 77 years old. He died doing mathematics. According to tradition, his last words were some variation of, "Don't disturb my circles." Whether he actually said this is unknowable, but it's perfect enough that it should be true. A man so focused on understanding that even imminent death was less important than finishing a proof. Marcellus did give Archimedes an honourable burial. He honoured the mathematicians' request and had a sphere inscribed in a cylinder carved on the tomb. Not the war machines, not the defence of Syracuse, the geometry. That's what Archimedes wanted remembered. The tomb was lost for over a century. In 75 BC, Cicero was serving as quaestor in Sicily. He'd read about Archimedes and decided to find the grave. He asked locals. No one knew where it was. Archimedes had been dead for less than 150 years, and his tomb was already forgotten, overgrown with thorns and brambles on the outskirts of Syracuse. Cicero finally found it by looking for the sphere and cylinder. He cleared away the vegetation, and there it was, exactly as Archimedes had requested. The inscription was still partially legible. Cicero was appalled that Syracuse had forgotten its greatest citizen, while Rome still remembered him. The story of Archimedes circulated through the ancient world in fragments. His mathematical works were copied, studied, sometimes misunderstood. His war machines became legendary, growing more elaborate with each retelling. Some sources claimed he built heat rays that set ships on fire using mirrors. This is probably false, or at least practically impossible, with ancient technology, but it shows how Archimedes' reputation had crossed from genius into something approaching sorcery. His actual mathematical work survived in scattered copies. The method that he used to calculate areas and volumes was largely forgotten or ignored because it was too advanced. Medieval mathematicians didn't know what to do with it. The techniques required understanding limits and infinitesimals, concepts that wouldn't be formalized for over 1,000 years. Then in 1906, something remarkable happened. A Danish philologist named Johann Ludwig Heiberg was examining a medieval prayer book in Constantinople. The book was a palimpsest, a manuscript where the original text had been scraped off and written over. Standard practice when parchment was expensive. Heiberg noticed traces of the original text showing through. He began to decipher it. What he found was Archimedes, a 10th century copy of works that had been presumed lost, including something called the Method, where Archimedes explained his technique for discovering mathematical truths before proving them rigorously. It was like finding Einstein's personal notebooks, showing how he worked through relativity before publishing the formal papers. The palimpsest contained Archimedes' actual thought process. He described how he used mechanical reasoning, imagining shapes as being composed of infinitely many, infinitesimally thin slices to discover relationships. Then he would construct geometric proofs to verify what his intuition had found. It was integral calculus, or the essential idea of it, 1700 years before Newton. Modern mathematicians reading The Method realized that Archimedes had been even further ahead than they'd thought. He wasn't just solving problems with techniques that wouldn't be formalized until the Renaissance. He was working at a level that wouldn't be matched until the 17th century. The sphere and cylinder proof alone would have secured his legacy. The work on pi was groundbreaking. His calculations of areas and volumes using what amounts to early calculus were revolutionary. But there was more, much more, that only came to light as scholars worked through the palimpsest and other surviving texts. Archimedes had thought about infinity. He'd developed a system for expressing extremely large numbers, something the Greek numerical system wasn't designed to handle. He'd calculated the number of grains of sand required to fill the universe, not because it was useful, but because it was an interesting problem that required inventing new mathematical notation. He'd studied hydrostatics, the behavior of fluids, and formulated principles that are still taught today. The legendary Eureka moment in the bath? That was Archimedes discovering that the volume of water displaced equals the volume of the submerged object, a principle now called Archimedes' principle. It seems obvious now. It wasn't obvious then. Every problem he touched, he transformed. That was his legacy. Not the war machines, though those were impressive. Not the defense of Syracuse, though that was dramatic. His legacy was showing what mathematics could do if you pushed it hard enough, if you refused to accept approximations when precision was possible, if you treated geometry not as a collection of known facts, but as a tool for discovering new truths. The man who wanted a sphere and cylinder on his tomb got his wish, at least for a while. The tomb was lost again after Cicero's rediscovery and has never been found since, but the mathematics survived. That's what matters. The proofs are eternal in a way that tombs never are. The mathematics survived, but the man behind it remained a mystery in most ways. We know what Archimedes discovered. We know almost nothing about how he lived day to day. No personal letters survived, no diary entries, no detailed biography written by someone who knew him. The ancient sources that mention him are sparse and often unreliable, written centuries after his death by people repeating stories they'd heard. What we can piece together comes mostly from fragments. Plutarch mentions him. Cicero describes finding the tomb, A few other Roman writers reference his work or his death, and that's essentially it. The historical record is thin enough that we can't even be certain about basic facts like whether he was married or had children. The silence is frustrating, but it also tells us something. In the ancient world, mathematicians weren't celebrities. They didn't have biographers following them around. Their personal lives weren't considered particularly interesting. What mattered, what got recorded, were the discoveries themselves. So we're left with the work, and the work is staggering. Start with something seemingly simple. How do you measure a circle? The Greeks knew the formula. The area equals pi times the radius squared. But where does that formula come from? Why is it true? Archimedes didn't just use the formula, he proved it. He showed exactly why it had to be that way. His method was to inscribe a polygon inside the circle and circumscribe another polygon outside it. The circle's area had to be somewhere between the two. Then he increased the number of sides on the polygons. More sides meant the polygons got closer to matching the circle. Keep going forever, and the polygons would become the circle. The area would be exact. This is limit reasoning. This is the fundamental concept underlying calculus. He was doing it in the 3rd century BC using only geometry and logic. No algebraic notation existed yet, no coordinate systems. He worked with pure shapes and pure reasoning. The calculation for pi used the same technique. Draw a circle, inscribe a hexagon inside it, calculate the hexagon's perimeter. That's your lower bound for the circle's circumference. Now circumscribe a hexagon outside the circle. Calculate that perimeter. That's your upper bound. The circle's actual circumference is somewhere between. Now double the number of sides. 12 sides gives you tighter bounds. Double again. 24 sides, keep doubling. Each step narrows the range. Archimedes went all the way to 96-sided polygons. The calculations were brutal without modern notation, but he pushed through. His final result? Pi is between 3 and 1/7 and 3 and 10/71. That's 3.1408 to 3.1428. The actual value is 3.14159. He'd nailed it to 2 decimal places using nothing but geometry and relentless calculation. The method of exhaustion, they called it. You exhaust the possibilities by squeezing closer and closer from both sides until there's nowhere left for the answer to hide. It's elegant, it's powerful, and it's painfully slow when you're working with polygons that have 96 sides and you're doing all the arithmetic by hand. But Archimedes did it anyway, because precision mattered more than convenience. His work on the spiral is another example. A spiral seems like a simple curve. Draw a line from a point, rotate it around that point while moving outward at a constant rate. You get a spiral, easy to visualize, extremely hard to analyze mathematically. Archimedes figured out how to calculate the area between one turn of the spiral and the next. He showed that the area equals 1/3 the area of the circle that would contain that section of spiral. That probably sounds abstract. Here's why it matters. To prove that relationship, Archimedes had to develop techniques for dealing with curves, for calculating areas bounded by curves, for reasoning about continuously changing quantities. These are calculus problems. He was solving them without calculus, as we know it. But the geometric reasoning he used contains the essential insights that would later be formalized into the calculus you learn in school. Consider the parabola problem. A parabola is a specific type of curve. Draw a chord across it, connecting 2 points on the curve. That chord and the curve enclose an area. What's that area? Archimedes proved that it equals 4/3 the area of the triangle formed by the same chord and the point where the parabola is steepest. He didn't guess this, he proved it rigorously. The proof required inventing new techniques for reasoning about curved shapes. He essentially created the method of integration, the process of adding up infinitely many infinitesimally small pieces to get a total. He didn't call it that. He didn't have the notation, But the concept was there, fully formed, waiting 17 centuries for someone to give it a name. The sand reckoner is different. It's not about geometry. It's about what happens when your number system breaks. The Greeks used letters for numbers, alpha equals 1, beta equals 2, and so on. It worked fine for everyday counting. It failed completely when numbers got large. Archimedes wanted to express very large numbers, numbers that the standard notation couldn't handle. So he invented a new system. He started with a myriad, 10,000. Then he built up a myriad myriads, a myriad myriad myriads. He created what amounts to exponential notation, a way to express numbers with many zeros without writing out all the zeros. Then he used it to calculate something absurd. How many grains of sand would it take to fill the universe? Not the Earth, the universe. The entire cosmos, as the Greeks understood it, with the fixed stars at the outer boundary. He had to estimate the size of a grain of sand. He had to estimate the size of the universe. He had to work out the calculation. His final answer was approximately 10 to the 63rd power. That's a 1 followed by 63 zeros. The number itself isn't the point. The point is that he could express it. The point is that he'd invented a system capable of handling numbers that large. The point is that he did it not because anyone asked or because it had practical value, but because it was an interesting problem. That's pure mathematics, solving problems because they're there to be solved. Plutarch tells a story about Archimedes and King Hieron. The king had commissioned a golden crown and suspected the craftsman had substituted some silver for gold while keeping the extra gold. The crown weighed the right amount, but was it pure gold? Archimedes supposedly solved this while taking a bath. He realized that gold and silver have different densities. If you submerge the crown in water and measure how much water it displaces, then do the same with an equal weight of pure gold, the volumes would differ if the crown contained silver. The story says Archimedes was so excited by this insight that he jumped out of the bath and ran naked through the streets, shouting, "Eureka, I have found it." Is the story true? Probably not in those exact details. It has the feel of legend, but the PR is real. The relationship between mass, volume, and density that Archimedes discovered is fundamental to physics. It's called Archimedes' principle now, and it explains everything from why ships float to how submarines control their depth. He wrote a treatise on floating bodies. It's one of the earliest works of physics, distinguishing between what we now call mass and weight, explaining buoyancy, analysing stability. A ship floats because it displaces water equal to its weight. A ship tips over if its centre of gravity rises above a certain point relative to the water. These seem like obvious facts now. They weren't obvious. Someone had to figure them out, explain them, prove them. That someone was Archimedes working in Syracuse while Rome was building an empire, and most of the world thought physics was just philosophy. The question that haunts historians is, what else did he discover that's been lost? The surviving works are fragments. We know this because ancient writers reference Archimedes' texts that no longer exist. There was a work on polyhedra, gone. A work on balances and levers, gone. A work on optics and mirrors, gone. We have approximately 9 complete treatises attributed to Archimedes. Ancient catalogues suggest there were many more. What was in those lost works? What problems did he solve that we're still unaware of? The Archimedes palimpsest gave us back the method and a few other texts, but it was one manuscript, and it was damaged, and much of it is still unreadable, despite modern imaging technology. Somewhere in the lost works might be discoveries that would surprise even modern mathematicians. Consider what we do have: the measurement of a circle, on the sphere and cylinder, on conoids and spheroids, the sand reckoner, on floating bodies, the method, on spirals, the quadrature of the parabola, on the equilibrium of planes. Each one contains results that were centuries ahead of their time. Each one required inventing new mathematical techniques. Each one solved problems that no one else had even attempted. And this is just what survived. The lost works might contain even more. There's a famous problem called the cattle problem. It's attributed to Archimedes, though some scholars doubt he wrote it. The problem is stated as a riddle. The sun god has a herd of cattle in multiple colours. The poem gives relationships between the numbers of each colour and type. Solve for the total number of cattle. The answer, when finally calculated using modern computers, has more than 200,000 digits. If Archimedes did pose this problem, and if he solved it, he was playing with numbers of a scale that wouldn't be seriously studied again until the 20th century. Even posing the question shows a mind thinking on a different level. His work on mechanics influenced his mathematics and vice versa. He understood that a lever allows you to move heavy objects because force multiplied by distance is conserved. Push down far from the fulcrum with less force, and you lift something near the fulcrum with more force. The distances balance the forces. This principle, which Archimedes formulated precisely, is conservation of energy in disguise. He didn't call it that. The concept of energy wouldn't be formalized for 2,000 years, but he understood the essential relationship. He even supposedly said, "Give me a place to stand, and I will move the earth." Whether he actually said it doesn't matter. The statement is mathematically correct. With a lever long enough and a fulcrum in the right position, you could theoretically move the earth. The practical problems are immense, obviously, but the principle is sound. That's Archimedes, taking an insight about levers and pushing it to its logical extreme, using mathematics to explore what's theoretically possible, even when it's practically absurd. His approach to problems had a pattern. Start with physical intuition. Use mechanical reasoning to discover relationships. Then construct rigorous geometric proofs to verify what intuition found. The method, the text recovered from the palimpsest, describes this process explicitly. He compared it to scouting terrain before battle. You explore informally to find the shape of the land, then you attack formally with full logical rigour. The informal exploration gives you the theorem. The formal proof gives you certainty. Both steps matter. Modern mathematics works the same way. Mathematicians experiment, try examples, develop intuitions, then they write proofs. Archimedes was doing this in the 3rd century BC, and he was conscious enough of his method to write it down and explain it. That self-awareness is remarkable. He wasn't just solving problems, he was thinking about how to solve problems. He was doing meta-mathematics before anyone had a word for it. The siege of Syracuse interrupted all of this. The mathematics stopped because war came. Archimedes turned his genius toward defense because his city needed him. The machines he built became his legend, but they also obscured his greater achievement. For 2,000 years, people knew Archimedes primarily as the engineer who built war machines, secondarily as the mathematician. Only in the modern era did the balance shift. Only when mathematicians recognized what he'd actually accomplished in his treatises did Archimedes the mathematician eclipse Archimedes the engineer. The weapons defended Syracuse for 2 years. The mathematics changed civilization forever. In 212 BC, the siege ended. Marcus Claudius Marcellus, the Roman general who had spent 2 years trying to break into Syracuse, finally succeeded. The city fell not through assault, but through betrayal. Someone opened a gate. Roman soldiers poured in during a festival when the defenders were distracted. The details vary depending on which ancient source you read, but the outcome was the same. Syracuse was taken. Marcellus had given orders that Archimedes was to be captured alive. The Roman general wanted to meet this man whose machines had killed so many of his soldiers, who had turned the siege into a nightmare of burning ships and crushed men. Marcellus recognized genius, even in an enemy. He wanted Archimedes brought to him unharmed. It didn't happen. The most famous version of Archimedes' death comes from Plutarch, writing 3 centuries later. A Roman soldier found Archimedes working on a mathematical problem. The mathematician was drawing figures in the sand, absorbed in some geometric puzzle. The soldier ordered him to come along. Archimedes, focused on his work, refused. He said something like, "Do not disturb my circles." The soldier, insulted or angry, or perhaps just following the general logic of a city being sacked, killed him. Other versions exist. One says Archimedes was carrying mathematical instruments to Marcellus when soldiers mistook them for valuable items and killed him for loot. Another claims he was trying to surrender but was killed before he could explain who he was. The consistent element across all accounts is that Archimedes died during the fall of Syracuse, killed by a Roman soldier, and that his death was contrary to Marcellus's orders. When Marcellus learned what had happened, he was reportedly grief-stricken. He gave Archimedes an honourable burial. He sought out the mathematicians' relatives and treated them with respect. The general who had besieged the city for 2 years mourned the man whose weapons had made that siege so costly. Archimedes had requested a specific memorial. He wanted his tomb marked with a sculpture of a sphere inscribed in a cylinder, representing his proof about their volumes. That theorem, the relationship between the sphere and cylinder, was apparently the achievement he valued most. Not the weapons, not the crown problem, not the calculation of pi or the areas of parabolas. The sphere in the cylinder, that was his monument to himself. The tomb was built according to his wishes. Then it was forgotten. Centuries passed. The Roman Republic became an empire. The empire converted to Christianity. The old Greek cities fell into decline. Knowledge was lost, texts burned, libraries destroyed. The tomb of Archimedes disappeared beneath weeds and neglect. Most of Archimedes' treatises were copied and recopied through the centuries. Byzantine scholars preserved them. Arab mathematicians studied them and built on them. When the texts reached medieval Europe, they exploded like delayed bombs in the minds of mathematicians who encountered them. Leonardo da Vinci studied Archimedes. Galileo called him superhuman. Newton built his calculus on foundations that Archimedes had laid. Every mathematician who has since worked with integration, with limits, with the precise calculation of curved areas and volumes, walks paths that Archimedes pioneered. But the transmission was fragile. The method, Archimedes' explanation of his problem-solving process, existed in only one known copy. That copy was written on parchment in 10th century Constantinople. Parchment was expensive. 3 centuries later, a monk needed parchment for a prayer book. He took the Archimedes manuscript, scraped off the mathematical text, and wrote prayers over it. The Archimedes palimpsest was created by destruction. For 700 years, the method was lost. Scholars knew Archimedes had written it because other ancient authors mentioned it, but nobody could read it. The prayers were visible. The mathematics underneath was invisible. In 1906, Johann Ludwig Heiberg examined the manuscript in Constantinople and realized what it was. Using photography and careful analysis, he recovered some of the underlying text. His work revealed the method and several other Archimedes texts that had been hidden beneath the prayers. It was an extraordinary recovery, but incomplete. The technology of 1906 had limits, then the manuscript vanished again. It resurfaced in 1998 at an auction house in New York. Its ownership disputed, its condition deteriorated. An anonymous buyer purchased it for $2 million and made it available to scholars. Modern imaging technology, including X-ray fluorescence and ultraviolet photography, revealed text that Heiberg couldn't read. The full extent of Archimedes' work on infinity and the foundations of calculus became clear only at the end of the 20th century. Think about that trajectory. A mathematician in 3rd century BC Syracuse develops methods that anticipate calculus. His work is preserved through copying. One copy survives. That copy is erased for prayers. The erased text is partially recovered in 1906. The full text is finally read in the 1990s using technology Archimedes couldn't have imagined. 2,000 years from creation to complete recovery. How much else was lost? The method survived by accident. What didn't survive? What did Archimedes write that nobody copied, or that was copied but all copies were eventually destroyed? We know he wrote more than we have. Ancient references mention texts that are now gone completely. The loss is incalculable, but also inevitable. Transmission of knowledge across centuries is always precarious. What survives is partly merit, partly luck. Archimedes' work survived because it was good enough that people kept copying it despite not fully understanding it. Medieval scribes copied texts about areas and volumes even when they couldn't follow the proofs, preserving the mathematics for future generations who could. The rediscovery of Archimedes in medieval Europe helped trigger the scientific revolution. When scholars finally had access to his treatises, they saw what was possible. They saw that geometry could be pushed beyond what Euclid had done. They saw that mathematics could be applied to physical problems in precise, powerful ways. They saw a model of mathematical thinking that was more sophisticated than anything else available from antiquity. Galileo's work on motion was directly inspired by Archimedes. The idea that mathematics describes physical reality, that you can use geometry to prove things about forces and weights and speeds, came from reading Archimedes. Newton's Principia, the book that founded classical physics, uses geometric methods that descend directly from Archimedean techniques. The calculus that Newton and Leibniz developed in the 17th century formalized ideas that Archimedes had explored mechanically. Newton even used a method he called the method of first and last ratios, that's essentially Archimedes' approach to limits. The conceptual breakthrough that calculus represents, the idea that you can handle infinity through rigorous limiting processes, was something Archimedes had understood 2,000 years earlier. He didn't have the notation. He didn't have the formal framework. He didn't have the concept of a function or the rules of differentiation and integration that students learn today. But he had the essential insight. He knew you could divide things into infinite pieces, add up the pieces, and get exact answers for curved figures. He knew you could trap areas and volumes between bounds that got tighter and tighter until they squeezed the answer into existence. That's calculus. Archimedes was doing calculus in everything but name. Modern mathematics finally caught up to him in the 19th century. Cauchy and Weierstrass formalized limits. Riemann developed rigorous integration. The foundations that Archimedes built intuitively were reconstructed with full logical precision, and when mathematicians looked back, they recognized him as the predecessor. The man who got there first with tools that shouldn't have been adequate, but were because his geometric intuition was so powerful. His influence extends beyond calculus. The Archimedean property, a fundamental axiom in modern real analysis, states that for any two positive numbers, you can always multiply the smaller one enough times to exceed the larger. It seems obvious, but it's actually a crucial assumption about how numbers behave. It's named after Archimedes because his work depended on it, and because he understood its importance. The Archimedean spiral, defined by the equation r equals a times theta in polar coordinates, is one of the first curves studied that isn't a circle or a straight line. Archimedes investigated its properties and calculated the area it encloses. Spirals now appear everywhere in mathematics, from complex analysis to dynamical systems. Archimedes got there first. His approach to problem solving influenced how mathematics is done. The combination of intuitive exploration followed by rigorous proof is standard practice now. Mathematicians experiment, conjecture, test examples, develop intuitions, then they prove. Archimedes described this two-stage process explicitly in the method. He formalized what good mathematicians do instinctively. Even his personality influenced the culture of mathematics. The story of him running naked through Syracuse shouting "Eureka" became the model for the lone genius having a sudden insight. the image of the absent-minded mathematician so absorbed in problems that he neglects everything else, that started with Archimedes being killed while drawing circles in sand. These stories are probably exaggerated or invented, but they shaped how people think about mathematicians and mathematical discovery. The weapons he built had no lasting influence. War machines get obsolete. The catapults and cranes that defended Syracuse were impressive for their time, but they didn't change warfare permanently. Siege technology moved on. What Archimedes did as an engineer was remarkable, but ultimately temporary. What he did as a mathematician was permanent. His theorems are still true. The proof that a sphere has 2/3 the volume of its circumscribing cylinder holds now as it held in 250 BC. The calculation of pi to multiple decimal places using inscribed and circumscribed polygons is still a valid method. The technique for finding areas under parabolas still works. The mathematics doesn't age. That permanence is what makes mathematics different from almost everything else humans do. Art styles change, political systems rise and fall, languages evolve, technologies become obsolete. But mathematical truth, once discovered and proved, stays true. The Pythagorean theorem is eternal. So is Archimedes' work. He proved things that nobody would prove again for 2,000 years. When mathematicians in the 17th century finally developed calculus, they discovered they were walking trails Archimedes had already walked. When 19th century mathematicians formalized real analysis, they found that Archimedes had anticipated their insights. When 20th century scholars finally read the palimpsest with modern technology, they found he'd gone even further than anyone realized. How far could he have gone if Syracuse hadn't fallen? If he'd had another decade or two of peace to work? If his texts had all survived instead of mostly being lost? We can't know. We only have what remains. And what remains is enough to recognize him as one of the greatest mathematical minds in human history. The last words attributed to Archimedes are, "Do not disturb my circles." Whether he actually said them is uncertain, but they're fitting. They capture something true about him. A man so absorbed in mathematics that, even with a city falling around him, even with a soldier standing over him, he was still working on a problem, still drawing figures, still thinking. That focus, that commitment to understanding, that refusal to be distracted from the work, even when distraction would have saved his life, that was Archimedes. The weapons were a side project. The crown was a puzzle someone asked him to solve. The real work was the mathematics, the circles in the sand, the theorems, the proofs. The soldier killed him anyway. The general understood what his men apparently didn't. That this old man drawing circles in sand was worth more than all the gold in Syracuse. That killing him was like burning the library of Alexandria. But the deed was done. Marcellus reportedly wept. He gave Archimedes an honourable burial and granted his family protection. Small consolations. The greatest scientific mind of the ancient world was dead at 75, killed by a soldier who didn't know what he'd destroyed. Syracuse fell completely. The Romans looted the city. They killed or enslaved most of the population. They took the treasures, the artworks, the wealth that had made Syracuse one of the richest cities in the Greek world. Marcellus kept his promise about one thing. He had a tomb built for Archimedes, marked with the symbol the mathematician had requested. A sphere inscribed in a cylinder. That was the diagram Archimedes wanted to define his legacy. Not the weapons, not the crown's story. A geometric proof. The demonstration that a sphere has exactly 2/3 the volume of its circumscribing cylinder. That was what he considered his greatest achievement. The tomb stood for generations. Then Syracuse declined. The city that had been a major power became a provincial backwater. The tomb fell into neglect. Weeds grew over it. Eventually nobody remembered where it was. 150 years after Archimedes died, Cicero was serving as quaestor in Sicily. The Roman orator and statesman had heard about Archimedes, had read some of his work, and wanted to pay respects at the tomb. He asked the locals where it was. Nobody knew. The greatest scientist in Syracuse's history, and the city had forgotten where they'd buried him. Cicero searched. He finally found it outside the Agrigentine gate, overgrown with thorns and brambles. He could barely make out the weathered diagram carved on top, a sphere and cylinder. He had the tomb cleared and restored. But after Cicero left Sicily, it was forgotten again. Today we don't know where the tomb is, it's gone. Somewhere under modern Syracuse lies a monument to the man who calculated pi and invented calculus 2,000 years early. But we've lost it. That loss is symbolic. Most of Archimedes' work disappeared. Of everything he wrote, less than 10 works survive. We have the major treatises on geometry and mechanics. We have On Floating Bodies and On the Sphere and Cylinder, and Measurement of the Circle. But we've lost what might have been the most important text of all. The method was gone for 2,000 years. It vanished sometime in late antiquity or the early Middle Ages. The manuscript was lost. Scholars knew it had existed because other ancient writers mentioned it. They knew Archimedes had written something explaining his techniques for discovery, but the text itself was gone. Medieval scholars studied Archimedes from what remained. Arab mathematicians translated his works into Arabic and pushed his ideas further. European scholars translated the Arabic translations back into Latin. A limited selection of his treatises circulated, enough to show he was brilliant, not enough to reveal everything he'd done. Then, in 1906, a Danish scholar named Johann Ludvig Heiberg was cataloguing manuscripts in Constantinople. He was examining a Byzantine prayer book from the 13th century, a palimpsest. That's a manuscript where someone has scraped off the original text and written over it with something new. Parchment was expensive. Recycling old books was common. Heiberg noticed something odd about this prayer book. Under the prayers he could see traces of older text, mathematical diagrams, Greek letters. He looked closer. It was Archimedes. Someone in the 13th century had taken a manuscript containing several of Archimedes' treatises, including the method, and scraped off the mathematics to write prayers over it. The prayer book had been used for 700 years. The original text was barely visible, but it was there. Heiberg spent weeks examining the manuscript with a magnifying glass, trying to read the faint traces of text underneath the prayers. He managed to transcribe most of it. What he found was stunning. The method explained how Archimedes actually discovered his results. It showed him using techniques that wouldn't be formalized until the 17th century. It revealed that he'd gone even further than anyone had realized. But Heiberg's transcription was incomplete. The text was too faint in places. Some pages were damaged, some had been cut out of the book entirely. Then the manuscript disappeared again. It surfaced briefly in Paris in the 1920s. A French scholar tried to photograph it, but the images were poor quality. Then it vanished. For most of the 20th century, scholars only had Heiberg's transcription. The actual manuscript was gone. Lost in some private collection, maybe destroyed, nobody knew. The greatest mathematical text from antiquity had been found and lost again, until 1998. The manuscript appeared at an auction house in New York. It had been in a private collection in France. The family was selling it. The Greek Orthodox Church, which claimed ownership based on the manuscript's origin, tried to stop the sale. They failed. An anonymous buyer purchased the palimpsest for $2 million. Then something remarkable happened. Instead of keeping it private, the buyer agreed to let scholars study it. Not just study it, apply every modern technology available to extract information from those scraped, overwritten, damaged pages. Teams of imaging specialists used ultraviolet light, infrared, multispectral imaging, X-ray fluorescence. They photographed every page under dozens of different wavelengths. They built software to digitally separate the layers of text. to enhance the faint mathematical symbols underneath the prayers, to recover text from pages that looked completely blank to the naked eye. It took years, but they did it. They recovered text that Heiberg couldn't read. They found sections that had been completely invisible in 1906. They discovered that Archimedes had done things nobody suspected. One of the recovered texts showed Archimedes working with actual infinity, not as a concept or a philosophical idea, but as a mathematical object he could manipulate. He was solving problems that required him to add up infinitely many, infinitely small pieces. That's calculus. He was doing calculus in 250 BC. Another recovered section showed him calculating the properties of the stomachion. Remember that puzzle? 14 pieces that can be arranged into a square in different ways? Modern mathematicians thought it was just a game. The palimpsest revealed Archimedes was doing something deeper. He was exploring combinatorics, counting the number of possible arrangements, working out problems in what we now call discrete mathematics. He'd invented another branch of math that wouldn't be formally developed for 2,000 years. The full contents of the palimpsest are still being analysed. Scholars are still finding things, still discovering that Archimedes went further than we thought. The man was so far ahead of his time that even with all our technology and knowledge, we're still catching up. Think about that timeline. Archimedes dies in 212 BC. His works circulate for a few centuries. Then they start disappearing. By the Middle Ages, most are lost. A few survive in copies of copies. The method is gone completely. Then in 1906, Heiberg finds it underneath prayers in a Byzantine manuscript. He transcribes what he can see. The manuscript vanishes. 92 years later, it surfaces at auction. Modern technology finally reveals what's really there. And we discover Archimedes was even more brilliant than we'd thought. How much more did we lose? What was in the texts that didn't survive? What problems had he solved that we'll never know about? The frustration is enormous. We have glimpses, fragments, enough to see the outline of what he achieved, not enough to see it all. But what we do have is extraordinary. The surviving works show a mind operating at a level that wouldn't be matched for 2 millennia. A mathematician who understood concepts that wouldn't be formalized until the 17th, 18th, 19th centuries, who asked questions that modern mathematicians are still working on. And here's the haunting part. He was one man, in one city, for 75 years, mostly working alone. With none of the tools we take for granted, no algebra, no coordinate geometry, no calculus textbooks, no computers, no vast libraries, no international conferences, no collaboration networks. Just him, wax tablets, sand, papyrus, a brilliant mind, and time. He figured out things that required armies of mathematicians 2,000 years later to rediscover. He solved problems that stumped the best minds in Europe for centuries. He proved theorems that looked impossible. He built machines that seemed like magic. He laid foundations that mathematics would eventually build on, once mathematics caught up to where he'd been. The question isn't how did Archimedes accomplish so much? The question is what was in the water in Syracuse? What combination of circumstances produced this particular genius at this particular time? We don't really know. Syracuse was wealthy. It had a tradition of supporting scholars. It was connected to the intellectual networks of the Greek world. Archimedes studied in Alexandria, absorbing everything known at the time, then came home and pushed beyond it. But lots of cities were wealthy. Lots of places supported scholars. Lots of students studied in Alexandria. Most didn't become Archimedes. Something about him specifically, some combination of ability, education, opportunity, and drive that created one of the greatest scientific minds in history. And then a soldier killed him while he was drawing circles. The waste is staggering. Not just the individual death, though, that's tragic enough. The waste of what he might have done. He was 75, but apparently still working. Still sharp. Still productive. What would he have discovered with another decade? Another 20 years? What problems was he working on when Syracuse fell? What manuscripts were lost when the city burned? We'll never know. We only have what survived. The fragments, the damaged palimpsest, the treatises that made it through the collapse of ancient civilization, through the Middle Ages, through wars and fires and neglect. A fraction of his total output, enough to recognize genius, not enough to see its full extent. But even the fraction changed mathematics forever. The ideas that survived influenced everyone who came after. Arab mathematicians in the medieval period built on his work. Renaissance scholars rediscovered him and were astonished. Early modern mathematicians realized he'd beaten them to discoveries they thought were new. 19th and 20th century scholars kept finding that he'd anticipated things they were just figuring out. Archimedes never stopped being relevant. His works never became obsolete. They just kept revealing new layers. Every generation of mathematicians reads him and finds something they didn't see before, some technique, some insight, some approach that turns out to be useful for modern problems. That's the ultimate measure of mathematical genius. Not just solving the problems of your own time, creating tools and ideas that remain useful thousands of years later. Work that doesn't age, truths that stay true. The sphere and cylinder on his tomb, that symbol he chose. It represented something profound. Not just a specific theorem, though that theorem is beautiful, but an approach, a way of thinking. The idea that you could understand the world through mathematics, that geometry wasn't just practical surveying or engineering, it was a way to glimpse eternal truths. 2,000 years later, we're still drawing circles in sand, still working out the implications of what he started, still finding his fingerprints on mathematics. The soldier destroyed the man. He couldn't destroy the work. That survives. Incomplete, fragmentary, damaged, but surviving. And still teaching us. Still showing us what human intelligence can achieve. Still pointing toward problems we haven't solved. The circles remain. And here's something most people don't realize. For nearly 2,000 years after his death, we didn't actually have Archimedes' most important work. The method was lost. Completely. Gone. The treatise where he explained how he actually made his discoveries. Not just the polished proofs, but the messy process behind them. The scaffolding before the building, it vanished sometime in the medieval period. Scholars knew it had existed because other ancient writers mentioned it. But the text itself, nowhere. Then in 1906, a Danish philologist named Johann Ludwig Heiberg was examining manuscripts in Constantinople. He found a prayer book from the 13th century. Nothing special. Except when he looked closer, he noticed something odd. Underneath the prayers, barely visible, were traces of older text. Someone had taken an ancient mathematical manuscript, scraped off most of the ink and written prayers over it. This wasn't vandalism. This was standard practice. Parchment was expensive. Old books got recycled. But this particular old book turned out to be a copy of several works by Archimedes, including The Method. The only copy that survived. If this one prayer book had been destroyed, and it nearly was, we would never have known how Archimedes actually thought. Heiberg spent years working on the palimpsest. The text was faint, damaged, partly destroyed by mold and water, but he could read enough to recognize what he'd found. The mathematical world was stunned. Here was Archimedes explaining his actual discovery process, and it was nothing like what anyone expected. In his published works, Archimedes presented perfect geometric proofs, rigorous, airtight, no hint of how he'd found them. The method revealed his secret. He used mechanics, physical reasoning. He imagined shapes as being made of infinitely thin slices, then used principles of leverage and balance to figure out their properties. It was brilliant and completely unorthodox. The standard Greek approach to geometry was purely abstract. You didn't think about physical objects, you thought about ideal forms. Archimedes ignored that. He used whatever tools worked. Then once he'd found the answer through mechanical reasoning, he'd go back and construct a proper geometric proof for publication. The mechanical method was just scaffolding. He threw it away once the building was done. Except he didn't throw it away. He wrote it down. He preserved his process in the method because he thought it might be useful for other mathematicians. He was teaching, showing his techniques, explaining not just what he'd discovered, but how to discover. And then we lost it for 19 centuries. When Heiberg published his findings, mathematicians immediately recognized the significance. This was Archimedes thinking out loud, working through problems, making mistakes and correcting them, using intuition and physical reasoning before formalizing everything. It was like finding Newton's scratch paper, or reading Einstein's diary while he worked out relativity. We got to see genius in process, not just in final form. But the story doesn't end there. The palimpsest disappeared again. After Heiberg studied it, it went back into private hands. It surfaced occasionally, changed owners. Then in the 1920s it vanished completely. For 70 years nobody knew where it was. Scholars who wanted to study it couldn't. The photographs Heiberg had taken were all that remained. In 1998 it appeared at a Christie's auction. Anonymous owner. The Greek government tried to stop the sale, claiming it was Greek cultural heritage. The Orthodox Church claimed it was theirs. The judge ruled the sale could proceed. A private collector bought it for $2 million and immediately did something unexpected. He made it available to scholars, funded a proper conservation and imaging project. The palimpsest was in terrible condition by this point. Not just the original damage from being scraped and overwritten. New damage too. Someone had added forged medieval paintings over some of the pages, probably to increase the value as an art object. Those paintings covered text. And there was mould, water damage. The binding was falling apart. A team at the Walters Art Museum in Bâle. Timur spent years working on it. They used every imaging technology available. Ultraviolet light, infrared, X-ray fluorescence. They could read text that was completely invisible to the naked eye. And they found more than Heiberg had seen. New sections, new theorems, new approaches. Archimedes kept surprising us even through a damaged medieval manuscript that had been scraped, overwritten, moulded, forged upon, and nearly destroyed multiple times. The resilience of his ideas is almost absurd. You literally scrape them off the page and write prayers over them, and they still come back. You add mould and water damage, and forged paintings, and they still survive. You lose them for 2,000 years, and they resurface. It's like the mathematics itself refuses to die. The palimpsest revealed something else too. Archimedes was working on infinity, actually working with it, using something very close to calculus. 2,000 years before Newton and Leibniz, he had a method for summing infinite series, for finding areas under curves by dividing them into infinitely many infinitely thin slices, for calculating volumes of complex shapes by integration. He didn't have the notation, he didn't have the formal framework, but he had the core insight, the limiting process, the idea that you could approach an exact answer by making approximations finer and finer without end. This is calculus, the foundation of modern mathematics and physics, and Archimedes was doing it in Syracuse in the 3rd century BC. Of course, he couldn't take it as far as Newton would. He didn't have algebra, he didn't have the coordinate system, he didn't have 2,000 years of subsequent mathematical development to build on, but he saw the path, he took the first steps. Then his work was lost, and mathematics had to rediscover everything he'd figured out. How much faster would science have advanced if the method had survived? If every mathematician from Archimedes to Newton had access to his techniques? We lost 2 millennia, because a prayer book was more valuable than mathematics. Though maybe that's unfair. The people who scraped off the text and wrote prayers weren't trying to destroy knowledge. They were preserving what mattered to them. They needed prayer books more than they needed ancient Greek mathematics. Their world was collapsing. The Byzantine Empire was under constant threat. Faith probably felt more useful than geometry, and they did preserve the parchment. If they'd thrown it away completely, we'd have nothing. The prayers protected the mathematics in a strange way, made it worth keeping even though nobody could read what was underneath. Still, the waste, the near loss, the fragility of it all. One manuscript, one copy. If it had burned or rotted completely, or been cut up for bookbinding, which happened to countless medieval manuscripts, we would never have known. Archimedes' act. UL thinking process would have remained a mystery forever, but it survived. Barely. Through luck and accident and the occasional person who recognized value in old things. Now it's digitized, fully imaged, available to anyone with internet access. You can look at the same pages Archimedes' ideas were written on, see the scraped text, read the mathematics. The most precarious survival turned into universal access. From one fragile manuscript that nearly disappeared multiple times to millions of digital copies that can't be destroyed. That's something Archimedes would have appreciated. The practical solution, the mechanical advantage. You can't preserve parchment forever, but you can copy information infinitely. Make it robust through redundancy, and the information is what matters. The theorems, the proofs, the methods, the insights, those don't decay. They don't mold. They can't be scraped away. Once you understand them, they're permanent. They exist in every mind that grasps them. That's what survived. Not the parchment or the ink, or even the specific words. The ideas themselves, the mathematical truths that Archimedes discovered, and that remain true regardless of who knows them or how they're preserved. 2,300 years after his death, students still learn his principle about buoyancy. Engineers still use his laws of the lever. Mathematicians still study his methods for calculating pi and finding areas and volumes. The work didn't just survive, it stayed relevant, active, useful. Most ancient knowledge became obsolete, got superseded by better understanding. Not Archimedes. His mathematics remained cutting edge for millennia. Still is in some ways. There are papers published now that reference his techniques, not as history, as working methods, as live tools for solving modern problems. You can't say that about many thinkers from any era, let alone from antiquity. The staying power is remarkable, and it reveals something about the nature of mathematical truth. It's not like other knowledge that depends on context or technology or cultural understanding. Once you prove something mathematically, it stays proved. The Pythagorean theorem was true before Pythagoras, and will be true after the last mathematician dies. Archimedes' calculation that a sphere has 2/3 the volume of its circumscribed cylinder doesn't become false just because civilizations collapse. The truth persists, independent of human awareness. We discovered it, we didn't invent it. That's what Archimedes understood. He wasn't creating mathematics, he was uncovering it, finding truths that were already there, waiting to be found. The eternal patterns underneath physical reality. The soldier who killed him destroyed a person. He couldn't touch the mathematics. That exists in a different realm, not in books or brains, but in the structure of reality itself. We just access it through books and brains. Lose the books and we lose access, but the mathematics remains, waiting to be rediscovered. Which is exactly what happened. We lost Archimedes, then mathematicians over centuries rediscovered his insights independently, proved the same theorems, developed the same methods, found the same truths because those truths were there to be found. The method just sped up the process by showing the shortcuts. But even without it, even with almost all his work lost, the essential ideas survived because they were too powerful to stay hidden. Other thinkers stumbled onto them, recognized their value, built on them. The chain never completely broke, and now we have most of it back. The palimpsest restored, the treatises preserved, the ideas alive in modern mathematics. Archimedes lives in every calculus textbook, in every physics class, in every engineering calculation. The man died in Syracuse. The work is immortal. That immortality raises a question. If the mathematics is what matters, if the ideas survive regardless of the person, then why does Archimedes himself still fascinate us? Why tell the story of the man at all? Because the mathematics didn't discover itself. It required a specific kind of mind, a particular combination of curiosity, rigor, and creativity that appeared in one person at one moment in history. Remove Archimedes from Syracuse, and maybe someone else eventually finds some of his results, but not all of them. Not in the same way, not with the same elegance. Genius isn't interchangeable. The method shows this clearly. Other mathematicians had studied areas and volumes. They developed some techniques, but nobody had Archimedes' insight to use mechanical reasoning as a bridge to geometric proof. That specific connection, that particular way of thinking, was his. It emerged from his unique perspective, shaped by his training in physics and engineering, as well as pure mathematics. You can see it throughout his work. The way he moves between abstract theory and concrete application, between ideal forms and physical reality, between what must be true and what can actually be built. Most ancient mathematicians picked a lane. Either you studied pure geometry like Euclid, or you worked on practical problems like the engineers. Archimedes refused the distinction. He lived in both worlds simultaneously. That dual perspective gave him advantages neither pure theorists nor pure practitioners possessed. The theorists could prove theorems, but often missed practical applications. The practitioners could solve immediate problems, but lacked the mathematical framework to understand why their solutions worked. Archimedes bridged the gap. He could derive the theory and build the machine. This made him dangerous to conventional thinking. Academic mathematicians of his era viewed practical application as beneath them. Real mathematics dealt with eternal truths, not mundane engineering. But Archimedes demonstrated that the eternal truths had immediate practical value, that you could use pure geometry to design better catapults. That understanding conic sections helped you build better mirrors for setting ships on fire. The burning mirrors, incidentally, probably didn't exist. Later writers attributed them to Archimedes, but the story is almost certainly myth. Focusing sunlight with bronze mirrors to ignite enemy ships makes for dramatic storytelling, but dubious physics. The engineering challenges would have been enormous, the tactical limitations severe. It's the kind of superweapon that sounds plausible until you actually try to build it. But the legend reveals something true, even if the details are false. People believed Archimedes could build such a weapon because he'd already built things equally impressive. The compound pulley system that supposedly let him move a fully loaded ship single-handedly. The water screw that efficiently lifted water for irrigation. The planetarium that mechanically reproduced the motions of celestial bodies. These were real, documented, witnessed. So when later writers wanted to explain how Syracuse held out so long against Rome, they reached for Archimedes, made him responsible for all the city's defences, turned him into a one-man military-industrial complex. The historical Archimedes probably contributed to the war effort, but he didn't personally design every defensive weapon. The legend inflated his role because people needed to explain the inexplicable. How did a single city resist Rome for 2 years? The answer couldn't just be competent generals and determined defenders. It had to be something exceptional. Someone exceptional. Archimedes fit the role perfectly. He was already famous, already credited with mechanical marvels. Easy to expand his legend to include military genius as well. This pattern repeats throughout history. Exceptional individuals become repositories for collective achievements. Newton gets credit for inventing calculus despite Leibniz developing it independently. Darwin gets credit for evolution despite Wallace reaching similar conclusions. The lone genius narrative is simpler than acknowledging the messy reality of multiple contributors and gradual development. But sometimes the lone genius narrative is actually true, or close enough to true that the simplification doesn't distort the essential facts. And Archimedes represents one of those cases. Yes, other people contributed to Greek mathematics. Yes, he built on earlier work. Yes, some achievements attributed to him probably weren't his, but the core accomplishments, the major breakthroughs, those were genuinely his. The method, the calculation of pi, the spiral, the principles of buoyancy and leverage, the integration techniques. One mind produced all of that. Which brings us back to the original question. Why does the person matter if the mathematics is what survives? Because we're not just preserving knowledge, we're trying to understand how knowledge gets created. How does someone look at a circle and see infinity? How does someone discover truths that weren't obvious to anyone before? How does the human mind reach beyond what's given and grasp what's possible? Archimedes provides a case study. Not the only one, but an unusually clear one because his personality comes through in the work. The playfulness, the confidence, the refusal to accept that something can't be calculated just because it seems impossible. You can see the person in the mathematics. Take the cattle problem. Archimedes sent it to mathematicians in Alexandria as a challenge. It's a number puzzle involving enormous quantities. The solution requires finding integers that satisfy multiple conditions simultaneously. The smallest answer has more than 200,000 digits. You can't solve it by trial and error. You need systematic methods, and Archimedes knew this. He designed the problem specifically to be solvable in principle, but impossibly difficult in practice. A mathematical trap. Solve it if you can, he's saying to his colleagues. I dare you. It's competitive, playful, showing off, very human motivations driving very abstract mathematics. Or consider how he ended his life, drawing geometric figures in the sand during a military invasion, telling a soldier to get out of his light. That moment crystallizes everything about him. The priorities, the focus, the total absorption in mathematical thought to the exclusion of physical danger. It's almost certainly embellished in the retelling, but it's emotionally true. Archimedes really was the kind of person who'd care more about a proof than a sword. These human details matter because they remind us that mathematics, for all its abstraction and universality, gets discovered by specific people with specific personalities in specific historical moments. The truths themselves are eternal. The process of uncovering them is deeply contingent. Change the person, and you change what gets discovered and when. Imagine Archimedes born in a different city, one without Syracuse's tradition of supporting scholars, or born to a poorer family without access to education, or simply born 50 years earlier or later, missing the particular constellation of existing knowledge that made his breakthroughs possible. Any of these changes might mean his potential goes unrealized. The mathematics would still exist in some abstract sense, waiting to be found. But would anyone find it? When? We can't know. History doesn't offer controlled experiments, but we can observe that certain kinds of genius appear rarely. That particular combinations of ability, education, temperament, and opportunity don't come along often. And when they do, the results can reshape entire fields for millennia. Archimedes reshaped mathematics, set it on a trajectory that led eventually to Newton and Leibniz, to Euler and Gauss, to all of modern calculus and analysis. He didn't do it alone, didn't work in isolation, built extensively on predecessors. But his specific contributions were irreplaceable. Remove them, and the timeline changes. Maybe we get there eventually, but not the same way, not as quickly, not with the same elegance. That's what we preserve when we preserve his work. Not just the theorems, but the approach, the way of thinking. The example of what's possible when a powerful mind focuses on fundamental problems. Every student who learns Archimedes' principle, every mathematician who studies his methods, isn't just acquiring information. They're connecting to a tradition, joining a conversation that spans centuries. And that conversation continues. Mathematics builds on itself in ways other fields don't. A modern biologist doesn't need to read Darwin's original work to understand evolution. The theory has been refined, expanded, superseded in its details. But a modern mathematician can still learn from Archimedes directly, can study his proofs, and find insights that remain relevant. This is what makes mathematics unique among human endeavours. The cumulative nature, the permanent validity of proven results. Every generation adds to the structure without demolishing what came before. We build higher, but the foundation remains solid, and Archimedes is part of that foundation. Bedrock that everything else rests on. The palimpsest reminds us how fragile that foundation was, how easily we could have lost it. One monk deciding to scrape away the text, one manuscript failing to get copied, one library burning. Any of these could have erased Archimedes from history. Not completely, some work survived through other paths, but large portions could have vanished forever. They didn't. Partly through luck, partly through the determined efforts of people across centuries who recognized the value of preserving ancient knowledge. The Byzantine scholars who copied manuscripts, the medieval translators who worked from Arabic versions, the Renaissance humanists who hunted for classical texts, the modern scientists who developed technologies to read overwritten parchment. Each generation did its part, and now we have the method back. Have most of what Archimedes wrote, can study his mathematics almost as completely as his contemporaries could. The chain of transmission held, barely. We came close to losing one of humanity's greatest minds. Didn't quite lose him. That's worth remembering. It's also worth remembering that we probably did lose others. How many ancient mathematicians wrote works we never recovered? How many insights vanished completely? How many potential Archimedeses never had their work preserved at all? We can't know the answer, can only recognise that survival was never guaranteed, that the accident of preservation shaped what knowledge reached us. We got lucky with Archimedes, lucky that enough survived to reconstruct his achievement, lucky that people kept caring enough to preserve what remained, lucky that modern technology arrived in time to read the palimpsest before it degraded beyond recovery. Luck, but also something more than luck. The mathematics itself exerted a pull, drew people to preserve it because the content was too valuable to lose. Bad poetry gets forgotten. Mediocre philosophy fades away. But genuinely important mathematics creates its own momentum. People recognize quality even across vast cultural and temporal distances. They work to preserve it because they understand, even imperfectly, that it matters. Archimedes mattered. His mathematics mattered. Still matters. Will continue to matter as long as humans study geometry and calculus and the fundamental patterns of quantity and space. The man died in Syracuse 23 centuries ago. The work remains alive, active, relevant. That's the real monument, not the tomb he was buried in, not the sphere and cylinder carved on his gravestone, not the legends that grew around his name. The mathematics itself, the theorems and proofs and methods that continue to teach, to inspire, to reveal truth. We tell his story because it's dramatic. A genius defending his city with mathematics and machines, killed by a soldier who didn't recognize what he was destroying. It's a good story. But the reason we still tell it isn't the drama. It's that the story is about something that actually matters, about the creation and preservation of knowledge, about human minds reaching toward truth and sometimes grasping it, about the long chain of understanding that connects us to the past and will connect us to the future. Archimedes grabbed hold of that chain and pulled it forward, showed what was possible, set standards that still challenge us. And his work, rescued from a medieval palimpsest, continues to pull us forward, toward deeper understanding, toward better mathematics, toward truth. That's what survives, not bronze or marble or parchment, truth itself, eternal, uncaring, patiently waiting to be discovered. Archimedes found some of it, showed us where to look, and the search continues.